wanted to talk about when we have our first test day.
Yes.
Didn't we say we were gonna do this today? With the
So,
other class. We
honestly don't remember.
we're past, we're.
Good days, Annie.
Yeah.
Let me just tell you this, so I let the class decide when they have their test. It doesn't matter, all right? You're gonna have this test. Normally, I would, what I have you do is discuss it and then we vote on it. We'll put two or three dates up. Right now, we've got only about 2/3 the class of that here. So how about Friday, first thing? We vote, first discuss it among yourselves, see when you'd like your first test. You get one test, and then you get the final exam plus all the quizzes, all right? And I'm planning to have a quiz Friday too. This has been a crazy time. We're off a week. Now we get two class periods and we're off Monday. And I'll do what I can do. Anyway, so first of all, any questions about the homework or anything else before I start? Nothing at all? I don't know if it's supposed to rain today or what.
11.
Wait,
It
it
is?
70%.
Maybe that explains the lack of participation. That or people just don't want to come back. They're on vacation. They're having a party. All right, whatever the reason, that doesn't matter. So today I'm going to talk about arrays. We went through and we did short dipole. We did a short dipole. We did any arbitrarily long dipole. Then we did the half wave dipole. We also did the small loop antenna. So we've covered more or less the common antenna types outside of parabolics, dishes and stuff, which is a little advanced. We've covered all of them. Now, and we talked about how to actually model what the antenna is. It's going to have a real and imaginary part, and we need to remember, this is the one thing that's important. Remember, for a half wave, if you cut it down, instead of being 0.5 lambda, if it's 0.485 lambda, then it's strictly real. There's no imaginary part to the antenna piece. That's one thing to remember. So now we're going to talk about arrays. And so this is array theory. Now, let me just say one thing about this with arrays. The real benefit is that instead of getting the power gain increased by a factor of n, where n would be the number in the array, it's n squared. So it goes up as a square. So normally what they do when they talk about array theory is they're going to say, I'm going to have a whole bunch of just single point isotropic radiators. And Whitworth's books does it a little different. Just there's n of them and they're spaced by d apart. All right, each one of these is going to be an isotropic radiator, and this is in a line, so these things are in a straight line. All right, and there's going to be n of them, so it goes from 1 to n. And we're assuming they're isotropic radiators, and I gotta say one other thing too. There are so many different variations of how current is established on an array like this. In Dr. Whitworth's book, he talks about a linear array being the most common. He's right. So the first one is going to have a current I naught. The second one will have a current I naught, but it'll be at some phase angle. So this is going to have a progressive phase shift with the same magnitude current. This one's going to have I naught e to the j2 alpha, I naught e to the j3 alpha, and then finally you can see this would be just I naught e to the jn alpha. Y'all follow me on this? It doesn't matter how many there are. This is how the currents are going to be. Same magnitude current, different phase. Now, I want to tell you this. In the real world, both the magnitude and the phasing can be varied. And usually what they do, they have something called a power coupler that ensures that the amount of power to each one of these antennas is as you want instead of the current. It's very hard to get the actual current you want because that's a function of voltage. And the impedance of this antenna, this is a stretch for you to imagine. If you talk about this being a dipole antenna right there, and you're driving it with a voltage, and you're trying to establish this current, well, the impedance it sees will be different than this one and this one. So you can't just use the same voltage. You have to, if you want the same current, you have to actually modify that. You all follow me, class? Anyway, so this is an isotropic radiator. Each one of these things, these dots right here, has a field. And we just call it E isotropic. We're gonna say that's just gonna be equal to the magnitude of the current at one of these things, whatever it is, over, you can put 4 pi r, you don't have to, and it's gonna have a phase shift e to the minus j beta r. And we're assuming r right here, r is much, much greater than nd, or the array length. And we're taking, I hope you can imagine this. I don't know in physics if you had something like this, but I think you might in optics, the optical thing. We'll call this R naught. And this goes a long way, it goes to some point a long way away. Follow me on this, guys? Think of it like 10 miles away, with this being of the order of a meter. Now this one, R1 here, is gonna have, well, I can call this, I'll call that R naught. Here, what we assume is that these two things are parallel to each other. And that the actual angle that radius vector r makes is going to be called phi. I hope you can appreciate this. So we've got, just think about this, we're talking about finding the electric field from these, and they're all assumed isotropic, and we know that really doesn't exist. It kind of does if you think about the sun or a star, but we have to use an isotropic radiator here because the way we get the final field is if we find the actual field pattern from this isotropic array and then we multiply it by the electric field pattern for any dipole or any kind of an antenna we put here, if they're all the same, then you get the total field pattern. So that's the reason for this. And I'm trying to isolate this one aspect of it. It's most complicated. So because of this, you can see that this right here, the distance difference between R naught and R1 is this distance here. And that distance, D right here, is going to be D times the cosine of phi. Can you all see that, class? This distance right here would be D cosine of phi. If that's D, and if you take the cosine of that, you get the projection on this vector. Does that make sense? Just think about it. And of course, when phi goes to 90 degrees, then the cosine phi is 0. There is no difference in the actual length. So R1, if I had to do this, I'll call this R1, R2, and R3, and so forth, R to the n. That's really going to be equal to R naught minus, and it would be the number n times d cosine of phi. And I hope you appreciate what I'm trying to show you is that parallel rays, each one of these is going to have a slight difference in length, and it would be equal to simply R naught minus d times the cosine of theta, but it would be the number of whatever number of the element. So anyway, that's the idea of this. Y'all follow me? Get a mental picture of what's going on? So now we're going to assemble the field out here at this distant point. And we're going to say E, and this would be from the isotropic radiators, will be equal to the E field from the first one. Well, the first one is just going to be I naught, right, over 4 pi r times e to the minus j beta r naught. Then plus the field from the second one, that'll be I naught, and I can put this as R naught here. I can put it as I naught over 4 pi, and here's the argument. Because R naught and R1 are almost the same. Think of the difference between a mile and an inch. Add an inch to it, right? There is no real difference in dividing by that. So you can just call this R naught if you want. Now up here we're going to have e to the minus j, it's beta, and here's where the difference happens because of the phase. This will become R naught minus d cosine phi here, and there'll also be that phase added onto it. Well, I'll have e to the j alpha. Then you're going to have plus I naught over 4 pi R naught. And then it's going to be e to the minus j, and then it's going to be 2 beta d cosine of phi, or I'm sorry, 2 times, yeah, beta d cosine of phi. Let me do it the other way. It's just twice this, so it's going to be 2 times, and then it's going to be beta here, and then it's going to be R naught minus d cosine of phi. I'm sorry, the 2 should be here. Plus 2 beta, and then it's R naught minus 2d cosine of phi. And this pattern's gonna repeat out to the nth term. Can y'all appreciate this? I'm gonna reduce the complexity next, and I hope you guys get a better understanding of this. All right. So next, you can see that a lot of stuff repeats. You see how the I naught appears in all of these, right? Yep.
Does that last term also have the e to the j alpha at the end?
Yeah, it does. It's gonna have e, but it'll be e to the j 2 alpha, right? And plus, I'm just showing you the pattern, the repetitive pattern. I'm gonna reduce the complexity. I'm gonna add a few things to make this more understandable. And this is done in Whitmer's book. So normally, when you see something that's repetitive, and I'm just gonna rewrite the symbols over and over again, you try to, make it simpler and easier to understand. So what they normally do is they'll talk about psi, and they'll talk about psi being equal to beta d cosine of phi plus alpha. Now remember, the phase shift is going to be progressive all the way down. Same amount of phase difference between all of them. So if this was 0 degrees, this might be 30 degrees, this might be 60, 90, and so forth. You all follow me on that, guys? All right. So I introduce this symbol, and then I can say that the isotropic radiation pattern is going to be equal to I naught over 4 pi, and I'm just going to call it R. You can call it R naught if you want. And then I can factor out an e to the minus j beta R, minus j beta R naught. You can call it R naught if you want. Now you see how that term is common to all of them. It's there, it's there, it's all the way down the line. Do you all see it? Now what am I left with? Well, the first term I'm left with just 1. The second term I'm left with e to the j, and then it's going to be beta d cosine phi plus alpha. So this is really going to be just psi plus e to the j 2 psi plus dot 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 plus e to the j n psi. And y'all follow what I'm doing. I hope that's not too much of a stretch. You see, if you expand this, you get e to the minus j beta R naught, right? And it will be times e to the plus j beta d cosine phi plus alpha. Do you all see that? And we just replace that e to the j beta d cosine phi plus alpha with psi. That's what this is for. Makes life easier. Okay? All right. Now I talk about this repetitive series. And I like to make sure you see this. This is one of the things, when you had, in your mathematics courses, you had geometric series, you had probably Maclaurin series, binomial series, you had all these things. This is an important one to remember. And I'm going to do it over here. What I'm about to show you. Now, who had me for signals and systems? Anybody? Well, if you didn't have me for that, you won't remember this, because I don't think you, well, maybe you can. All right, so if we have a series like summation of a to the n from n equals, say, 0 to some n minus 1. You all follow me what I'm doing? Well, that really can be written as what? Just 1, because when a to the 0 is 1, plus a squared plus a cubed plus dot 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 plus a to the n minus 1. You all agree? All right. Now, if I take that, right, and I'm going to take that same series, I'm going to put a to the n equals 0 to n minus 1, but now I'm going to multiply it by a. Y'all follow me? I'm taking this and I'm going to multiply it by a. I'm going to rewrite it down here. That means it would be a plus a squared plus a cubed plus dot 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 plus a to the n. Y'all follow the progression? You're wondering why I did that, because now I'm going to subtract. If I subtract this, right, from that, then I'm left with 1 minus a There's 1 in front of there, there's a minus a there. And then I would have the sum of a to the n from n equals 0, pardon me, 0 to n minus 1. And that would be equal to, and here's where the magic happens. So I have 1 minus, there's no 1 down here, so there's going to be a 1. Then I have a minus a goes away. A squared minus a squared goes away. A cubed minus a cubed goes away. Y'all follow me? All the way down except for a to the n. That one survives. Sorry, my writing's so bad. So I can see that this series, I have 1 minus a, and remember, I took that series and I subtracted this from it, or I have 1 in front there minus a, right here, times that series, which means that actual geometric series right here of a to the n from n equals 0, n minus 1 is equal to 1 minus a to the n over 1 minus a. And that's a closed form. Doesn't matter how many terms in that series. Y'all follow me? That's the answer to it. Do you remember doing this at all in your math classes? They had all sorts of clever tricks they showed you to evaluate series. And usually you look for repetitive patterns in some way to get an addition or subtraction to get rid of terms every term. All right, so this is it. So this is the series, what it converges to, and this is important. Now I come over here. My series right here, all right, this is actually I naught, right, over 4 pi, doesn't matter if you call it R naught or just call it, times e to the minus j beta R naught. And then it's times this, really. It's a series, and here it would be from n equals 1, no, actually from 0, because that would be a 0, to, and then you could say it's n minus 1 if you have n terms of e to the j psi, or n psi, pardon. It's e to the j, e to the j small n times psi. Do y'all see that would be that series of summation? Take a good look. I'm just trying to make sure you at least appreciate the math on this part. All right, now, what is that really? If you come back over here, I can say the series over there is simply 1. It's the summation of quantity e to the j psi to the nth power, where n goes from 0 to n minus 1, isn't it? If you take a careful look, just the summation, take a look. You agree? Well, this e to the j is like a, e to the j psi, which means this thing actually goes down to 1 minus e to the j n times psi over 1 minus e to the j psi. And I'm just following that recipe right there. Y'all follow me? I'm trying to be clear about this. The reason we need to this geometric series is we've got to get to that finite result, so it doesn't matter how many elements, and then we're going to modify that result in a second. Are you all with me on this one, guys? You may not like it, but try to appreciate it, all right? It's necessary to understand array theory. Okay, now remember, psi itself is beta d cosine phi plus alpha. It's not a real angle. It's something that is used as just a condensed terms there. Y'all follow me? I take this, and now I'm going to modify it. This is one of those things that you'll learn to appreciate the reason you turn everything into trig functions. And the reason you do is because you understand them. You know what a sine function looks like, right? You know what a cosine function looks like, or a tangent. Those you can imagine. You can't imagine that. I don't know what that is. All right, so what I'm going to do is factor out on the top an e to the minus j n psi over 2. That means I'm left with e to the j psi n psi over 2 here, and it'd be minus e to the minus j actually, sorry, it should be e to the j. You should factor out an e to the j n psi over 2. And then I would have e to the minus j n psi over 2 minus e to the j n psi over 2. And then the bottom, I'm going to factor out an e to the j psi over 2. And I'd have e to the minus j psi over 2 minus e to the minus, or I'm sorry, e to the plus j psi over 2. Can you all follow me? Look, if you take this, e to the j n psi over 2 times e to the minus j n psi over 2, you get 1, right? So that's the factor. Now, anybody want to take a guess why I did that?
So you can turn it into cosines and sines, you said, what was it?
It would actually be a sine, but you're exactly right. Now, I'll show you up here. Take a look at this. Remember that in Euler's identities, the sine of theta was equal to e to the j theta minus e to the minus j theta over 2j. Y'all remember that? Right. Look here. If I can factor out a -1 on both of them, so I make this negative, make this negative, then this becomes plus and this becomes minus. Y'all see that? Now, why did I do that? Because that's e to the j n psi over 2 minus e to the j minus j n psi over 2. It fits this form perfectly. And that would be 2j times the sine of that angle. Y'all follow me? Take a careful look. Just try to appreciate, I'm trying to fit this form. I'll multiply this by 2j. And now if you look there, I have e to the j n psi over 2 minus e to the minus j n psi over 2. It fits this form exactly, and the theta in that would be actually n psi over 2. So now, I'm going to replace this over here. And I'm going to say that the negatives cancel, so I have e to the j. And then, if I take this upstairs, it would be n minus 1 times psi over 2. And then here, I'm going to have 2j sine of this argument there. Downstairs, 2j sine theta, the 2j's cancel, so I get the sine of n psi over 2 divided by the sine of psi over 2. Now just take a look at that for a second. I'm just showing you what that series condenses to. Y'all with me? Now this is an interesting function. How many remember what the sinc function is? All right. What, you remember, you'll have signals and systems.
Isn't it like that goes up and then down or something?
Yeah,
Like the curve?
sinc function is one of the more important functions that, I mean, in engineering, you use it all the time. There's two ways to write it, but generally speaking, the sinc of the function x is really the sine of x over x. And what that looks like, if you plot it versus x, is this. And let me plot the magnitude of the sinc of x. It looks like this. All right? How many remember that? All right, that's the sinc of x. All right, and this would have a value of 1 here. Now, this isn't exactly the sinc of x, but remember, if you have sine of x is about equal to x for small arguments of x. Do y'all remember that, class? How many do? If you have sine of x, you have a say sine of 0.01 radians, it's about equal to 0.01 radians, all right? In other words, the sine is about the argument for very small values. Well, for small values of psi over 2, this is about like a sinc function, and it's very similar to a sinc function. All right, and it looks very much like that. Try to appreciate that. It means you can imagine it when you're doing certain antenna engineering problems. It's much easier to understand, and you can find the nulls and things like that very easy. But that's what this function comes down to here. So now, over here, and what I'm going to do is I'm going to reduce that series and just replace it with that right there. try to get a little better board space here. It's gonna be one of the days. So I'm just gonna erase that, and I'll go ahead and place this with e to the j, and it's n minus 1 over 2 times psi, and then it's times the sine of n psi over 2 divided by the sine of psi over 2. Y'all follow me? Now, here's where I'm trying to explain this without confusing. You all see at least what I'm trying to accomplish. I'm trying to condense the complexity down so I have something manageable, something I can understand. And I can imagine if this is your first time viewing this, you're really wondering where in the world that we're going with this. You'll see in a second. All right, now, that was the actual electric field that we assumed isotropic radiators. And what you can see it breaks out to is you get the actual electric field from the element. In our case, electrostatic, or it was an isotropic radiator. So this is the elements field. All right. Can you appreciate that? That's what each element would radiate by itself. Follow me on that, class? This is really the effect of the array. So this, I call this the array factor. And it assumes that the currents are the same value and there's a progressive phase shift of alpha. Do y'all follow? That's the only thing I'm assuming here. But that's actually, the linear array is probably the most common array to start when you understand array theory. And it's used everywhere. It's in Whitmore's book, he does this. He spends more time doing just 2 or 3 antennas that are vertical dipoles and getting the electric field in a more complicated way. I'm just trying to say, the whole 9 yards of it breaks down to the total electric field from any array is going to be element pattern, which I used as isotropic, times this array factor. Now I need that board to get to some of my conclusions about this. At first, this looks a bit overwhelming and daunting, but it won't be in a second. Imagine a few problems. So, when I take a look at this, I made the case that if we have any array at all, and it doesn't matter what the elements are, and we have from 1 to n elements, all spaced by d, should have just left that drawing up. With currents, progressive phase shift I naught e to the j alpha, I naught e to the j 2 alpha, I naught e to the j n alpha, like that. And I want to know what the electric field is from these, with some angle phi at a great distance r. And if we know what the elements are, it doesn't matter what they are, I can say the electric field pattern at a distance, and this would be E total, would be equal to the electric field pattern of the element. And then it would be times e to the j n minus 1 over 2 psi times the sine of n psi over 2 divided by the sine of psi over 2. Y'all follow me on that? I'm just rewriting it, stating it explicitly. This is the array factor, and I'll break it out. My array factor is simply equal to e to the j n minus 1 over 2 psi. That times the sine of n psi over 2 over the sine of psi over 2. Now, you'll see this becomes very important. If we had, this is the total electric field, what would the power density be at any range? If we're talking about, this is for free space propagation. What do you know P-av is always? Average power is far field, free space.
1/2 electric field.
Magnitude of E squared over eta naught, and it would be in the radial direction, right? Y'all agree with that? Okay, now, the thing to note there, it's proportional to the E field squared. Y'all see that? All right, if I take the E field magnitude squared, just notice this. This term right here is just phase, isn't it, class? That e to the minus jn minus 1. This thing right here is just a phase. It's e to the j some angle. Do you follow me? So when we take the magnitude squared, that term goes away. What you actually get is this. The average power density is going to be equal to 1/2, and you can put the eta naught here. And then when you square the E field, you're going to get the element pattern squared. Doesn't matter what it is, whatever the angular variation is, a function of r, you're going to square that value, but then it's going to be the array factor squared, which is going to be the sine of n psi over 2, sine of psi over 2, magnitude squared. So the power density is going to be the power density that you would get from one of these antennas multiplied by that guy. Y'all follow me? And that's squared. Now, I gotta spend a little more time talking about this. I'm gonna say this, in Whitmore's book, make sure you put this down, in Stu's book, he has F equal to that. The sine of n psi over 2 over the sine of psi over 2. Right. Squared. So when he says he will use some terms there. He'll call it the array effect or array factor, something like that. That's what he has. In truth, what I like to, I think this is more common, they call it the array factor, is usually proportional to the actual sine of n psi over 2 times psi over 2, because it's what you multiply the electric field by. What he does is, in Stu's book, he uses the thing you multiply the power density by. Now, a little bit more on this, something that, so you can appreciate some of the things about this. So, if I take a look at a magnitude of just the sine of n psi over 2 divided by the sine of psi over 2, we'll prove it. The value at 0, graphing versus psi here, the value at 0 will be n times that, and it'll look like this. If you just take the magnitude and do this. Very similar to a sinc function. Y'all follow me? So the peak is increased by n when psi is 0. Y'all follow me, guys? That means the power density over here, if that's proportional to this squared, it means the power density increase will be n squared, the actual power density of just one element. All right, so the array does this. It magnifies the peak power density possible at range by a factor of n squared. If you got 100 elements, that's a factor of 10 to the 4th, 10,000 times as much as if you had a single element. That's the reason arrays are so powerful. You can also do things called beam stereo, and we'll get to all this, but I want you to just appreciate the mathematics and what happens. Now, the next logical thing is to understand that's how it affects power density. And in fact, because gain and power density, remember when we talked about a single antenna? We said if we had any single antenna right here, and if you knew the actual or the power that it's transmitting right there and hit it, gain and G, then if you're at a distance R away, the actual average power density was equal to the transmitted power over 4 pi R squared. That would be the isotropic spreading of power. And then it would be multiplied by the gain, whatever the gain is. It sharpens it, right? Well, what happens, the effect of this antenna to the gain is, it increases the gain of a single antenna by n squared. And that's one of the important things. Not by n squared. So if you have 10 antennas, the actual peak power density, all say 71 watt or something like this. The amount of power density increase, the peak power density increase, will go up by a factor of 100, not by 10. You all follow me? That's the important thing about this. And so the gain, the effective gain goes up by that much. So next, after that, let me show you how some of this would work in terms of a practical situation. I want to tell you, we don't get really deep into antenna theory in this class, but I haven't taught antennas, I don't think, here. I haven't taught out the book. Riggs used to teach antennas. When he retired, I don't know who's going to teach, but antennas is a good course. I want to also say one other thing. This fall, I'm teaching an EMC course, and we do a lot of stuff that's electromagnetic compatibility and interaction. I understand there's not that many people enrolled yet, and it may not fill up, but in there, what we do is we take all aspects of like electromagnetics, antenna stuff, and engineering, everything that you deal with Wi-Fi, routers, and all that stuff. And what we end up doing is solving problems and designing systems with the whole 9 yards considered. Now, if you're interested in that, consider that course. Riggs's course in antennas, usually in the spring, I think he teaches it. I don't know who's going to teach it. If I teach it, then we go really into a lot more detail in this, and you get a lot more depth in the way arrays work and other antennas and how you actually design it. But for now, what I'm going to just show you, there's 2 things always in engineering we do. First is analysis. Remember, you had circuits? You had to analyze circuits. You had to understand what the net effect would be if you connected things in a certain way. That was analysis. As you go through engineering, you learn synthesis, how to design to meet certain requirements. Now I don't know if you've done that in your labs. Did you have design laboratories or not? Where you had to design something that produced a certain level of amplification. You did? In what course?
We sort of did that in Digitron or even the radio lab.
All right. Design is the thing you're going to be paid a lot of money to do in the real world. You are engineers, and that's what they want. They don't want physicists that just can write equations and understand what happens and stuff. What they want is somebody that, if given a set of conditions that have to be met, you can create something. With antennas, it's very important. But before you do design, you have to know analysis. So the best way for me to show you how all this thing comes together is give you a very simple problem. I'll put one up here and we're going to analyze it, all right? So here's what I'm going to do. I'm going to take 2 elements, just 2 elements, and I'm going to say that these are both half-wave short dipoles. So I'm going to put it like this. They're going to be short dipoles, but they're situated in this way. And make them both of length, just L, and L is going to be much, much less than lambda, short dipoles. This one will have a current I naught, and this one will have a current I naught. Now, the array itself, this is important. These 2 are what they call the array line, or the actual, I guess they just call it the array most of the time. There's 2 elements, so n would be equal to 2. And if I'm going to get the far field, if this is R, right there, we call this R minus d cosine theta, if you want, but you don't have to. This would be the angle that we're in now. And what I want to do is figure out what the actual field would be from these things. I'm going to do something here too. I'm going to include it, no, tell you what, no, I'm not going to do it yet. I'm going to include a phase in a second. But y'all see we got that problem, right? All right, so the electric field from this, the E field far forward, here's where you have to be careful. I have to get the E field of the element first. Now take note. All right? Normally if we have a short dipole, like so, all right, and we talk about a radius vector R, the angle that's of interest is right here. Right? And we can say that the electric field that this has a current I naught at any given range first, just a short dipole would be J beta I naught, right, over 4 pi R. And then it would be E to the minus J beta R, but then it would be the sine of theta, it would be in the A theta direction. If you don't remember that exactly, just trust me. Y'all remember that field? I mean, now that I put it up there, it rings bells. It's a function of sine of theta, right? But theta is measured from the vertical. Now you notice how I oriented my dipoles? The angle, the array angle, is phi here, but I need to write it in terms of this theta, right? Y'all follow me on this? I'm going to use this as my angular variation right there. Got me, guys? And we're talking about the electric field on the plane of the board. I don't want this, you could take that and turn it into a conic section, but I don't want to go there. So it's just the electric field at a range in the plane of the board. Follow me? Okay, so now the electric field from the element would be J eta times beta times I naught would be over 4 pi R, would be times E to the minus J beta R. But now instead of the sine of theta, you see how that becomes the cosine of phi? Take a look there. All right. What I have, if you take a look at this, I'm trying to draw this in a way that would be meaningful. All right. If this is phi and this is theta, then if you look at this is radius vector R. The cosine of phi, right? The cosine of phi would be adjacent versus R, would be equal to the sine of theta, which would be the opposite of this over theta, over R. Do y'all follow? Sine is what? Opposite over hypotenuse. Cosine is adjacent over hypotenuse. Isn't it, class? Do y'all remember that? So I can write this as now cosine. Just play with it. You'll see this. I'm adapting. I could write this angle. I could say theta is really what? It could be 90 degrees minus phi, right? Couldn't I do that? And then I could take the cosine of, sine of 90 degrees minus phi, and you're going to find out it's cosine. I'm going to leave it like that. Then I multiply times the electric field, or the array effect, which is E to the J. Now N is 2, so 2 minus 1 is 1. So it's really psi over 2 times the sine of n psi over 2. N is 2, so it's just psi over the sine of psi over 2. Are you all with me? I'm trying to show you how you would do a field plot with this. And to be frank about what you're going to do is you're going to create a MATLAB program to do this, because I'm not going to have you longhand this stuff. It's insane to do it longhand, but you have to at least get an appreciation for it. So now I have this, and what I really care about is how this stuff varies with angle, but I'm going to get the power density first, because the power density is the most important. So when we get the average power density, that's 1/2 magnitude of E squared over eta naught in the AR direction. So I can say PM on this one will be equal to, now here's where I take all these terms. Remember, E field squared, that J goes away. The E to the minus J beta R goes away. I'm left with some constants, and I'll put them here. So I'm going to be left with eta times beta times I naught over 4 pi. As such, all that is gonna be squared. Then I'm gonna have a 1 over r squared here from that. And then I'm gonna have cosine of phi squared times the sine of psi over sine of psi over 2 squared. And that would be in the AR direction. Can you follow me on that, guys? I'm just trying to show you, I'm taking this thing, squaring it, and well, I need to divide by actually 1 over 2a to not 2. But all this isn't gonna matter. Now try to appreciate, I got all this junk, all these constants I'm squaring and dividing by and stuff. But ultimately, that is like a value, just some p, call it p naught. I can say it's just some p naught, right? That's just the constant divided by r squared, right? And then it's gonna be times this angular variation. It's gonna be times the cosine squared of phi times the sine of psi over 2, sine of psi, or sine of psi, over sine of psi over 2 squared. And that would be my p average right here. It's a little messy, and I'm sorry about that. Now I'll show you what's of importance. All right, now, if you take a look there, this is the angular function. And what they normally do when they do what are called power pattern plots. So when they do power pattern for arrays or any antennas plots, they normalize the power at a given range. So they want to take the normalized power density and plot it. But really what they want to do is take a look at how it varies angle in terms of the angle. In our case, it's phi and psi, and I'll get to that. So all this in front goes away. So now we're talking about plotting this function. And you can call it f of phi. And that's going to be equal to cosine squared of phi times the sine of psi over the sine of psi over 2 squared. We're going to plot that. Versus the measurable angle is actually phi. And remember, psi is equal to beta d cosine alpha, or I'm sorry, cosine phi plus alpha, right? Now just bear with me on this one. When I started this, the separation distance here is going to be d. Okay. I didn't tell you what d is. So now I'm going to say d is equal to lambda over 2. That's just arbitrary. And initially here, alpha, the phase shift was 0 degrees. So now I come back over here, and I say my psi is now equal to beta d. Well, beta is 2 pi over lambda. D was lambda over 2 times cosine of phi plus nothing, because the phase change is 0. Now, if you look at this, you understand I'm just putting beta is 2 pi over lambda times d is lambda over 2. I set that. I want to just take a look at the plot. You see the lambdas cancel, and then I have really pi times cosine of phi equals psi. Can you all see that? With me on this? Now, Now what I'm gonna do, or attempt to do, this is gonna be versus phi, and this is gonna be the sine, the magnitude of sine of, and it's gonna be pi cosine phi over sine of pi over 2 cosine of phi. What is this? And I'm going to plot that squared. So I'm plotting this angle right here versus phi. Just bear with me on this one. This may not be fun, but you're going to have to just focus on this. All right? Now, if you look at this for a second, really, what I need to do is evaluate this for certain angles. So I start with phi equals 0. When I have the cosine is 0, that's 1, right? Times pi. Sine of pi is 0, right? Down here, I have the cosine of phi is, cosine of 0 is 1, right? Because we're plotting. And then, but it's pi over 2. So what's the sine of pi over 2? 1. So 0 divided by 1 is 0, isn't it, class? It means when phi is 0, this function is 0, right here. Now, if you increase phi, if you let phi be equal to, you can say 45 degrees, all right? Bear with me. So if I have cosine of 45 degrees, that's 1 over square root of 2, right? Then I have it times pi. So, I would do that to myself. So then I have, it's finite. It's a finite value. This is going to be 1 over square root of 2. I should pick a better number. So this is less. What I'm going to show you is it's increasing. Sorry about that. This is 45 degrees. Now, where this becomes a maximum is, you can figure this out for yourself, is when this goes to 0 and this still remains finite. And what it'll do is this. I'm not gonna go through all this with you right now, but it'll basically look like this type of thing right here, and this will be actually 90 degrees. It's where the peak occurs, and this will be 180 here. Now, if I take that, and then on top of that, I have to plot this one. I know this seems a little troublesome, but you can do this. You can do this with a computer program very easy. Right? MATLAB, you can plot this thing in a heartbeat. You just create this function, and really, I'll put it down here for you. Really, what I'm plotting is this. F is equal to cosine squared of phi times the sine of pi cosine of phi over the sine of pi over 2 cosine of phi. I'm plotting this whole thing squared. That's really what I want to plot. Well, I've just plotted the top part. I've just plotted this right here. Now, if you plot below it the cosine squared of phi, and take a look at it, what is, I'm just going to plot, remember this is versus phi, so if I plot this versus phi, and put the cosine squared of phi here, you can see what happens. When phi equals 0, it's 1, right? Then, at 90 degrees, it goes to 0. I mean, this is going to be at 90 degrees, it's going to be 0. And it'll come back up again. Now what you effectively do is take these two patterns and multiply point by point to get the total pattern. And I'm going to tell you right now, looking at this, well, I'm thinking from your perspective, you're not seeing the way it looks. All right? Not from this, but I'm going to show you if you do this with a polar plot, it'll look a lot more understandable. Let me show you here. please pay attention to this. This is not gonna be loaded with math, it's gonna be loaded with what, how you go about understanding this. So if I have just dipole antennas like this, all right, just a dipole antenna, I know the field pattern for a dipole antenna, if it's a polar plot, and I look at my dipole this way, it will look like this. This is the power pattern. The actual power, normalized power pattern, will be equal to the sine squared of theta. Y'all follow me? Because the power would be proportional to sine squared, because the electric field is sine theta, right? That's our variance. So this would be the power pattern. Do y'all follow me on this? We did this when we got directivity. We had to get the normalized power pattern, and then we had to do what? Integrate that times sine theta, d theta, d phi from 0 to 2 pi, divide that into 4 pi to get the maximum directivity. But I'm just telling you, we've kind of covered this. That's the power pattern for these short dipoles. Now, with the array, this might be a little harder for you to see, but with the array pattern for these two things, they have actually, there's no phase difference. The array pattern will have nulls this way. So I'm superimposing, this is going to be the array pattern of F, of theta. And it will look like this. It'll be 0 that direction. It looks like this. Can you all follow me? When you actually plot this, you're going to get that pattern versus, and I'm measuring phi from here. Now, when you multiply them, just follow it. In your mind, you should be able to see this. Anywhere there's a null, like there's a null in this direction, vertical direction for the actual normalized power pattern, the element, you're gonna have a null. Try to do it right here. So I know I'm gonna have a null there. There's gonna be nothing there. I'm gonna have another null in this direction where the actual array factor, the F theta, is a null. By a null, I mean its value is 0 in that direction, at 90, or at phi equals 0 degrees. Do you follow me? So if you multiply, what you can almost see happening is this. You're gonna get this kind of a clover. There'll be 4 leaves to it. And the reason is I'm multiplying those two patterns together. Now in the real world, I'm gonna level with you. In the real world, your element pattern is the thing you first look at if you have an array. I know for instance, if these are halfway dipole or short dipoles or any straight dipole, I know directly above they irradiate 0. Do you all follow me? It means the array can never radiate vertically up here. The second thing is, I know they have a relative maximum in the horizontal plane, right? Now, then I take that and multiply it by the array factor, and the array factor takes a little time to get a handle on how to do these things, but you can do it mathematically. You can do that very easily with a computer. But that's the essence of really array theory. Right? Now, the things you really glean from this is the array allows you to increase the peak value of the power density by n squared if it's a linear array. Same value of current and just equal phase changes, right? There's a constant phase change. It effectively makes the gain go up, maximum gain by n squared. This is the key. Now, the actual pattern of these antennas, you can do something called beam steering, and we'll talk about that on Friday's class, but what we can do is take this antenna, and by changing the phase, we can steer and change this pattern. And I'll show you this stuff. I'll bring my computer down here and show you some things on Friday. So if we have a lot of these elements, we can actually get a very narrow, what's called a main beam, and we can steer it. And this is the real thing, the power of the array itself. It'll allow beam steering by just changing the phase on the actual elements. I'm thinking to myself, if I'm sitting where you are, probably the thing I need to see most is problems that first I'd be required to solve on a test or on a quiz. That's usually the first thing you think about. And second, something that's meaningful in terms of a real world application. So. Looking through the book. I wanna just see. Showing me. What I've just showed you is on page 471 of his book. It's equation 8.95. And he uses, instead of just the E field, he uses the power pattern. He has F, really he's calling it the unit pattern of the element times the array factor. He calls F sub array in his book. And he shows you on page 472 a plot of a dipole pattern in the horizontal plane for these arrays. Look at this. And then what I just did is the n-element linear array is on page 474. And equation, if you can write this down, 8.101 is the actual equation where you get the sine squared of n psi over 2 divided by sine squared of psi over 2. It is the most famous. It's the one thing everybody uses when they solve arrays, linear arrays. I'm going to give you some homework problems to do. I think on Friday, let me consider it, but I want you to do these things with MATLAB and then take a look at how he does it, but you'll find out these power patterns are some things that really you can do very easily with a computer. You can actually see the patterns for that. And we'll talk about beam steering too. Then. Now, the next thing, this is the one thing I want to cover also, is something that's important. It's called the Friese transmission equation. I know we just did a bunch of stuff with array theory, and until you do these problems, and use a computer to do some of them at least, if not most, you won't have an appreciation for everything that we've talked about. But once you do them, you will. I'll give you that. But now I want to talk about the Friese transmission equation. Now, I've got about 10 minutes, and that's just the amount of time I need. So, because this is necessary for some of the other things. So, this is a different section. It's called the Friese transmission equation. So here's how it works. If you have an antenna, doesn't matter what the antenna is over here, and the antenna is going to transmit a power PT or P trans. So that's the power transmit. Now the antenna has a certain gain, and the gain is a function of probably theta and phi, doesn't matter. And now I have a second antenna a distance r away. And this would be, I'll say it's the gain of the transmitting antenna. This is going to be the gain of the receiving antenna. It's a function of theta and phi. And what I want to do is find out how much power is received. Alright, so that's the goal of this. Are you all with me? I'm gonna go through this kind of slowly and methodically, but I wanna make sure you see this. You'll see how this works with the antenna array stuff in a bit. So I'm transmitting a certain amount of power, and it's got a transmitter gain. And I want to figure out, first of all, what the power density is out here. So I'm looking for a P average. What is the power density that is incident on this antenna? So the average power density would be equal to the transmitted power divided by 4 pi r squared. Now that's isotropic radiation. Then I have to multiply that by the gain of the antenna, which is a function of the angles. So then I multiply this by the gain of the transmitter. That's a function of theta and phi. Now that would be the power density right here. You all follow me? With me on this, class? Now, what we're going to do is talk about something, and it is the effective aperture, or the electrical size of an antenna. So write this down, the electrical size. It's also called the aperture of the antenna. And its symbol is A, usually AP, but it could be A sub E too. The aperture of the antenna is equal to lambda squared over 4 pi times the gain of the antenna. Now that's just the standard thing. It tells you how big it is electrically. If you know the gain of an antenna and you're talking about how big it is electrically, that's how you get it. And the reason we say this is because when you talk about how much power is received, what you need is the aperture of the antenna, or the size, electrical size, times the incident power density. That will give you the amount of power received. Power density is watts per meter squared. If we multiply that times meter squared, or an area, then you get the amount of power received. And this is how you do it. You're using this antenna, this is really the size of the actual receiving antenna. So if that's the average power density incident on this, then I can say that the actual power received, or the amount of power received by that second antenna, is going to be that power density. So it's P transmitted over 4 pi r squared. Then it's times gain of the transmitter, and it's a function of theta and phi. Then it's times the electrical size, which is going to be lambda squared over 4 pi times the gain of the actual receiving antenna. And that's a function of theta and phi as well. Can you all follow me on this? I just took the power density, I multiplied by the electrical size, and that's what that lambda squared over 4 pi g is. This is an important one too. So the way they usually do this is, when they talk about the Priest equation, they get the ratio of P received, the received power, to the transmitted power. Right? And that will be equal to, and it's really lambda, this is interesting when it comes out, over 4 pi r, then you square that quantity and multiply it by the gain of the receiver as a function of theta and phi times gain of the transmitter as a function of theta and phi. Y'all follow me? And this is first. This is the equation. This is really important. So, now to do a simple example of this. I'll do it right here. If I have a short dipole right here, yeah, I'll have a short dipole here. Yeah, short dipole. And I'm going to say this short dipole, it's hooked to some generator, and it's transmitting. I'm going to give you the P transmitted from this is going to be 500 watts. Okay, so I'm transmitting 500 watts. Now, in a straight line away, at a distance r equals 1,000 meters, I'm gonna have a half-wave dipole. Here, this one's gonna be lambda over 2. And I wanna know how much power is received by this antenna. Now, that isn't the amount of power that you can actually extract, but we'll get to that later. But you all follow me on this? So, this is the kind of problem on Friday. Hint, this is the kind of problem on Friday I'd expect you to do. And I'll give you problems with it. So, P received here would be equal, first you take the transmitted power, that's 500 watts. Then I divide by 4 pi r squared. That would be, really, I put 1,000 just squared so you know exactly what I'm doing. Now, remember, when we talk about the gain, peak gain of, or the gain of a short dipole, or directivity of a short dipole is a function of theta, that's 1.5 times sine squared of the angle theta, right? And the angle theta would be measured from the vertical axis to the radius vector. Y'all follow me on that, guys? All right, well, if I'm at 90 degrees, the sine is going to be 1, is it? So it's 1 times 1.5, that's the gain. It's times the max gain. Now it's going to be times lambda squared, or really, lambda over 4 pi r. I need a lambda, so I'm going to say that, I'll just say lambda is 1 meter. All right, that's 300 megahertz, okay? So I'm giving you effectively frequency and wavelength. So now I put down 1 over 4 pi, or really, I can actually do it this way. I can say P received is P transmitted, and then it's going to be times gain, the gain of the, or I'll put it as 1 over 4 pi, and R is 1,000 times 1,000. I'll do it exactly this way. Take that, square it. Gain of the transmitter is 1.5, it's peak gain, and this is broadside, so it's going to actually receive a maximum amount of power, and the gain of a half-wave dipole is 1.64. You remember that? For a half-wave dipole, the peak gain is 1.64. For a short dipole, it's 1.5. If you don't, I understand we had a long break, but that's what they relatively are. That transmitted power here was 500 watts, so I put 500 here. And that would be the amount of power received. That's how this equation is used. Now, there's a few things, I'm about out of time, but I gotta say it too. When you talk about these things, there's these antennas, the angle, like if this thing was raised, it would change the amount of power received, obviously, because the gains would then be different because of the angular difference. But this is real important here. If you take a straight wire antenna like this, and you transmit, the electric field is oriented in this direction. Do you all follow me? If you try to receive it with an antenna oriented this way, it'll get nothing because it's trying to induce currents along the antenna. And if the receiving antenna is not in the same direction, there's a polarization misalignment that we'll cover on Friday. Do you follow me? So, the way I set this problem up is as simple as possible. I assume both of these are directly in line for max gain, and they're also oriented in the same vertical direction, okay? If this thing was shifted this way, it would get 0. And the effect is actually, whenever you take something and you tilt it like that, it's called the tilt angle, and we'll get to that on Friday too, because I'm about out of time. And it's going to be times of the cosine of the tilt angle squared, would be effectively reduction in power. But I'll talk about that next. Anyway, that would be the amount of power that you receive. That's a simple one. For Friday, I'm going to give you some problems to do. I'm trying to get a quiz, I'm trying to get a simple quiz in. I need a break. I mean, it's been a long time since you've had one. It will be related to freeze, but it'll be a simple kind of problem, and I'll give you problems with both of these, okay? And I'm contemplating giving you a MATLAB homework for, to hand in to, just, I almost never do this, but just to make sure you've gone ahead and done this stuff. All right, and then I'll use that as maybe a bonus or something, if that's all right with everybody. Now listen, I know this array stuff. It can seem overwhelming, but it's not that bad. When you get the problems and take a look at this, it will not be that bad if you have a computer solution. You all know how to use MATLAB, right? You got a MATLAB? Or you use MATLAB, maybe not had it. You can use Octave if you want, MATLAB, but don't write it in Python. I have kids do that. All right, class is over, unfortunately.